please enter the class at the right time. Okay, I start the class by sharing the book. Okay. Let's share it again. The internet doesn't work properly, so we should wait until the problem is solved. Do you remember the last page we were studying? Anyone remember the last page we were studying previous week? No one remember? Okay, so I try to find it. Okay. I remember you studied the closed graph theorem and okay, you start from this theorem. Suppose x and y are Banach spaces and T is a bounded linear transformation from x to y. The following are equivalent. T is invertible means there is an operator we show by t minus power minus 1 such that t or t power minus 1 equals I. So t is invertible and the image of t is dense in y. It means that the image of When we say that the image of T is dense in Y, it means that the image of T closure is Y. So it means that image of T bar equals Y. In this case, we say that the image of T is dense in Y, and there exists positive alpha such that the normal fix is greater than or equal alpha normal x for all x. If these conditions satisfy, then T is invertible, and if T is invertible, we have these conditions. Corollary. Suppose that x and y are Banach spaces and T is a bounded linear transformation from x to y. Then operator T is not invertible if and only if image of T is not dense in Y, or there exists a sequence xn in x such that the normal xn equals n for all n, but the limit of T xn equals 0. If one of these conditions holds, then T is not invertible. Here is an example. If for any h in C of 0 and 1 means the set of all continuous functions from 0, interval 0 and 1 to C, and T of h be in L be on L power 2 of 0 and 1. These all integrable function on 0 and 1, and B of L power 2, 0 and 1 means the bounded operators on this space. If f is a function in C of 0 and 1 defined by f of t equals t, means f be identity function on 0 and 1, interval closing interval 0 and 1, then T of f is not invertible. This is a difficult example, really. So we pass for this. Another example like the previous example, but f here is another function. It's not identity function. This function is defined by f of t equals 1 plus t. In this case too, T of f is not, in this case, T of f is invertible. So here T of f is invertible, but the previous example, T of f was not invertible. This is also a little difficult. Example, another theorem that this theorem is also important. Let U and X be Banach spaces, and suppose that S is a non-empty set, and for each S in S, T of S be a bounded linear transformation from U to X. If for each U in U, the set of the norm of T S U for S in capital S is bounded, then this set is bounded to the norm of T of X, T of S. This is the operator norm, but these norms, this is the norm of a measure of X. And this is also difficult. Corollary, let U and X be Banach spaces and Tn belongs to B of U and X for all n from 1, 2, and etc. Suppose that the limit of T and U exists when n approaches to infinity for each U in capital U, and we define Tu as the limit of T and U when n approaches to infinity. Then T is also a bounded linear transformation from U to X. Here is some exercises. I will send the solution to you. Not all exercises, but okay. The last pages was this page, duality and Banach theorem. Dual space. Here is a special function. We call it Kronecker delta or delta function. Delta function is a function with two indexes, delta of j and k. When these two indexes are equal, delta equals 1. And when they are different, delta equals 0. Theorem. If X is a finite dimensional norm linear space with the basis V1, V2, Vn, then X prime means all the functions from X to F. Here, if T is a linear function function from x to f, f means the field of scalars, then t is called functional. And all functionals on x is denoted by x prime. And we call x prime as the dual of x. So x prime x is the b of x and f. So x prime here, the dual of x, has a basis like f1, f2, fn, such that fj of vk equals delta jk. It means that fj for vj equals 1, but for other vk, that k is not j, equals 0. So we have dimension of x prime equals the dimension of x, because if the basis for x is v1, v2, vn, it means that the dimension of x is n, so the dimension of x prime is n2, because f1, f2, fn with this equation is a basis for x prime. So in a finite dimensional vector space, x, the dimension of x and x prime are the same, but not necessarily in infinite dimensional vector spaces. Another important theorem is Rie's space, Rie's theorem or Rie's-Frechet theorem. Here, this is also an important theorem. Now we should wait. Okay. Okay. This is an important theorem. Unfortunately, internet doesn't work good. Okay, I hope I can write this important. Let H be a Hilbert space and F be in H prime, means F be a functional. On H, then there exists a unique Y in H such that f of x equals the inner product x and y for all x. And moreover, the norm of f as an operator norm equals the norm of y. So we can say that h equals h prime. In this view, h and h prime are the same because there is a one-to-one correspondence between h and h prime, and with this equation we can say that h is equivalent to h prime. So as in a sense, h prime can be identified with h. So we can write h equals h prime. H is when H is a Hilbert space, H and H prime are equivalent, and we can write H equals H prime. Another theorem, let H be a Hilbert space, and we define T of H from H to H prime by Thy equals Fy. Fy means Fy means the functional f that is correspondence with y. Fyx equals the inner product of x and y. So Fyx means the inner product x and y. In this theorem, we want to say that h and h prime are equivalent, or we can write equals. For a Hilbert space H, we define T of H from H to H prime by Th y equals Fy for all y in H. Then TH is a bijection, means a one-to-one and onto operator, and for all alpha, beta as scalars, for members are F, and all members Y and Z in H, we have TH of alpha Y plus beta Z equals alpha bar TH Y plus beta bar TH, and the norm of THY equals the norm of Y. In addition, the inner product in H prime can be defined on H prime by this. The inner product THZ and THY equals Y and Z in H. Here the places of Y and Z are exchanged. Here is THZ and THY, but here is Y and Z. Okay. Lemma for an arbitrary integer k, a positive integer k that is more than or equal 1, let Sk be a substub L infinity consists of the form x equals x1 to xk, and the other places are zeros, and S equals the U of xk means the all is k from 1 to infinity. The union of is k, then S but less than infinity, but not in L infinity. So this S as a union of Sk is dense in all LP, but it's not. So this is dense in LP for all P. Instead for all P but infinity. For all P, for all P, but it's not dense in L infinity. Another theorem, this is also a very important theorem. Important. This is an important theorem. Suppose that P is from 1 to infinity but not equals infinity, and if P is greater than 1, we can, for Q equals P over P minus 1, and if P equals 1, we define Q as infinity, to be infinity. If AN is in LQ, then for any X in LP equals the sequence Xn in LP, the sequence Rn Xn is in L1, and this function f(ax) equals the sigma of An Xn for all X in LP. This defines a linear functional in LP prime or LP prime, such that the normal Fa equals the normal A in Q, LQ. Here 1 over P plus 1 over Q equals 1. Here the dual of LP equals LQ. B. If f is a function in LP prime or a function on LP, then there exists a unit A in LQ such that f equals Fa. By parts A and B, the function Tp from LQ to LP prime defined by LPA equals F. A for all A in LQ is a linear isomorphism. So it means that LP prime equals LQ when 1 over P plus 1 over Q equals 1. As I said, this theorem shows that for P from 1 to infinity but not infinity, and Q is in theorem like this, 1 over P plus 1 over Q equals 1. LP prime can be identified with LQ. Here L1 is identified theorem below shows that L1 is not isomorphic to L infinity prime. A little strange. Okay, so in the case when P equals 1, the theorem doesn't hold for Q equals infinity, so L1 is not isomorphic to L infinity prime. Okay. I think we can finish the class here. Please remember the page. So Tuesday, if I forgot the last page, please remember this page and tell me to continue the class from this page. Okay. Any question? The class will be started at 3:30, not 4 o'clock. And enter the class at 3:30. This week we will have 2 sessions, today and Tuesday. Okay, so if there is no question, I finish the class and I say goodbye.